Some of the biggest problems in science and engineering boil down to a pretty simple question. When does a function equal zero? Now, that sounds easy, right? But for a lot of equations, you just can't solve them with simple algebra. So we need these really clever algorithms to hunt down the answer. So today, we're going to pit two legendary methods against each other in a race to find that zero.
So think about this for a second. What on earth connects the GPS in your phone, the complex models that try to predict the economy, and the math that lands a rover on another planet? I mean, they seem like they're from completely different universes.
But it turns out they all share this deep mathematical secret. At their very core, all of them need to find the roots of some incredibly complicated equations. And a root is just, well, it's the input to a function that makes the output exactly zero. It's that spot where the graph literally crosses the zero line.
So the fancy term for this is root finding. We're basically on a hunt for that one special value, that X star that solves our puzzle. And to find it, we're going to use what are called iterative methods. These are algorithms that start with a guess and then get closer and closer with every single step, just like a race to the finish line.
Okay, first up in our race is the slow and steady competitor, the one we'll call the tortoise, the interval bisection method. And its whole philosophy isn't about being fast, it's about being sure. The way it works is actually pretty brilliant. It traps the root. Imagine this, you're on one side of a river and your friend is on the other. That means the function is, say, positive on your side and negative on their side. Well, you know that somewhere in between you, the ground has to hit water level, right? That's the core idea. The algorithm makes sure the root is trapped and has absolutely nowhere to hide.
And you can see that trapping right here in action. The algorithm kicks off with this wide bracket. It checks the middle point and figures out which half the root is stuck in. Then boom, it just throws away the other half. Now the bracket is half the size, and it just does this over and over again. Chop, check, chop, check, squeezing the search area down until that bracket is unbelievably tiny.
And the algorithm itself? Oh, it's beautifully simple. First, you find that starting bracket where the signs are opposite. Then you calculate the dead center. Check the sign there, and depending on what you find, you shrink your bracket. That's it. You just keep doing that until you've zoomed in as close as you possibly need to be.
So what's the catch? Well, the tortoise's biggest strength is that it's just so reliable. If you set it up right, it is guaranteed to find a root. But its weakness is that it's slow, really slow. Its convergence is linear, which kind of means it just gains maybe one correct decimal place with each step. It just chugs along reliably, but without any exciting bursts of speed.
All right, now it's time to meet our other contender, the hare. This is Newton's method, and let me tell you, it is built for speed. It's powerful, it's elegant, and, well, it can be a little bit reckless.
So instead of just chopping an interval in half like a brute force method, Newton's method uses calculus to make a super intelligent guess. Wherever it is, it figures out the slope of the function right at that point. That's the tangent line. And then it just asks, okay, if I follow this straight line all the way down, where does it hit the zero axis? And that spot becomes its next, much better guess. And wow, this image just shows you the raw power of that idea. Look at the starting guess, x0. The algorithm finds the tangent and falls it down to get x1, which is way closer to the real root. Then from x1, it does it again, getting to x2. You can literally watch it accelerate towards the answer. This is called quadratic convergence. What this means is the number of correct decimal places can, double with every single step. It's insane.
But you know what they say, with great speed comes great risk. The hare is not perfect, so what happens when its clever little strategy completely backfires?
I mean, look at this. On the left, you see a perfect run, a thing of beauty. But on the right, that's what happens when it all goes wrong. If you give it a bad starting guess, or the function just has a weird shape, the tangent line can shoot the next guess even farther away. Or worse, like you see here, it can get trapped in an endless loop, just bouncing between 2 points forever, never actually finding the root. The hare can get totally, completely lost.
Okay, so we've met our racers. We know their game plans. Now it's time for the main event. Let's put them head-to-head on the exact same track and see who wins.
And the track for this race is going to be this polynomial equation, x cubed minus 2x plus 2. We can see pretty quickly that the function is positive at -2 and negative at -1, so we've got our starting bracket for the tortoise. All right, racers, to the starting line. Let's see how they do.
All right, let's break down the play-by-play. In the bisection column, you see that slow, steady, predictable progress just inching closer every time. Now, look at Newton's method. Whoa, what a shaky start.
That second guess sends it way off to -3. It looks completely lost. But then, boom, it course corrects. By the fourth iteration, it's back in the game, and then it just hits the accelerator. By iteration 6, its guess is already way more accurate than bisections. The hare, after a terrible stumble out of the gate, has won the race.
So, the takeaway here is pretty stark. When Newton's method actually works, it's not just a little bit faster. It's often more than twice as efficient, maybe even more in terms of how many steps it takes. That is a massive difference in performance. But you always have to remember that risk of it failing to work at all.
Okay, so this whole race thing brings up a really practical question, right? For any of these algorithms, how does it know when it's actually won? How does it decide that it's close enough to the finish line to just stop? Well, here's a mind-bending little fact. Computers aren't actually perfect at math. They store numbers using a limited number of ones and zeros, which means there are always these teeny tiny rounding errors. So, if you tell a computer to stop only when the function is exactly 0, that's a disaster waiting to happen. It might skip right over the true root by some infinitesimal amount and then just run forever, searching for a perfection it can never find.
So, since perfection is off the table, programmers use something called a tolerance, a way of defining what close enough means. They might stop when the distance between the last guess and the new guess gets super tiny, or they might stop when the function's output value is practically 0. And, this is crucial, they always build in a safety net, a maximum number of tries, just in case the algorithm gets lost, like our hare, and gets stuck in a loop.
And this isn't just some made-up problem. As the source material points out, if a function gets really flat near its root, those tiny little computer errors can get magnified and cause all sorts of instability. And that is especially dangerous for Newton's method, since it depends entirely on the function's slope to find its way. It turns out, managing the finish line is a real art.
So let's call it the final results of our epic race. In one corner, you've got the tortoise, the bisection method. It's guaranteed to finish the race. It is slow, it is steady, it is the safe bet. And in the other corner, you have the hare, Newton's method. It wins fast if it wins. It's powerful, it's complex, and it is the ultimate high-risk, high-reward play.
And all this leaves us with one final, really important question. In the real world, you can't afford to be slow, but you really can't afford to fail. So what's the solution? Well, the smartest programmers don't actually choose one or the other. They create hybrid methods that start with the reliable tortoise to safely box in the answer, and then they unleash the lightning-fast hare to pinpoint the finish line. They get the best of both worlds, proving that in the race to find 0, the real winner is the one that knows when to be the tortoise and when to be the hare.